We're going to revisit our unit circle today for a couple of minutes. So here we go. I'm in standard position, and now I'm going to rotate to there on my unit circle. Now, keeping in mind that this is the unit circle, that means that hypotenuse that I just drew in is a length of 1 unit. Now, my reference angle, the distance between that terminal side and the x-axis is right there. There's my theta. And if I draw my triangle in here, my right triangle, now we have some x distance, some y distance going up to that point that's on the circle. Now keep in mind though, x and y with trig, x is really the same thing as the cos of the angle, and the y, the up and down, is the same as the sine of the angle. So this little triangle here is going to be used to develop what's called a Pythagorean identity. Because on a right triangle, we can set up Pythagorean theorem. And on this triangle, I know the hypotenuse is 1, so that's going to be my c value. And then my two legs are cos theta and sine theta. So I'm going to do cos squared theta plus sine squared theta. And we all know 1 squared is the same thing as 1. And this is our main Pythagorean identity. Cos squared plus sine squared equals 1. And that's going to be true of any angle of rotation that we do. I'll prove it for we'll call it a 60-degree angle. So I plugged in 60 for theta. Now notice here, I picked values that we actually know, degrees that we actually know exact values for. So the cos of 60 is 1/2. So if I take that and square it, that's going to be 1/4. The sine of 60 is radical 3/2. And if I square that value, I'm going to get 3/2 squared, which is 4. And that all is supposed to equal 1. And notice 1/4 plus 3/4 is equal to 1. So it checks out. And again, not only would that work for 60 degrees, it'll work for any angle theta that you choose. One of the other nice things that the Pythagorean identities can do for us is if we are simplifying a trig expression where we see ones and squares, one of the Pythagorean identities might be able to substitute in, just like we subbed in yesterday the quotient and reciprocal identities. So this equation can be manipulated algebraically to become whatever we want it to be. For example, if I want this to be cos squared equals something, I can use algebra to make this equation become cos squared equals 1 minus sine squared. Likewise, if I want this equation to become sine squared equals something, I can subtract the cos squared over to the other side. And we get sine squared is equal to 1 minus cos squared. So let's look at this example, cos minus cos times cot. And I want to simplify this down to one trig function. So we're going to start plugging in our reciprocal or quotient identities. So cosecant is the same thing as 1/sin. Cos we're going to leave as cos. And cot we're going to use cos theta over sine theta. Now, following order of operations, I need to multiply before I subtract. So when I multiply cos times cos over sin, that's going to be cos squared theta over sin theta. And now I'm ready to subtract, and this worked out conveniently because I have a common denominator already. So my common denominator will stay sine theta. And my numerator, 1 minus cos squared, not like terms, so I'm just going to leave them like that. 1 minus cos squared. But notice 1 minus cos squared, this 1 minus cos squared is the same thing as sine squared. So I'm going to substitute in that Pythagorean identity right here to make it sine squared over sine. And then, look how nice this is. The sine on the bottom cancels out one of those two signs on the top. So that entire expression we started with, cosecant minus cos times cot, is the same thing as doing just sine theta.